Welcome to part 2 on talking about the definite integral. Our next example says evaluate or find the exact value of the definite integral from -2 to +2 of the function 3x minus x squared plus 2 dx using the Riemann definition of the definite integral. So first off, I just want to say, if you're watching my videos or you're in one of my classes and you ever see this icon, that means that you can actually click that icon if you're on the digital file or the PDF file, which all of these notes, the PDF files, you can find on my website. So if you ever encounter this icon here, that means that you can click it and it'll take you to my YouTube channel where I go over either that exact example or one very similar to it. So in this case, I go over an example on my YouTube channel that is very similar to this example. It's not the exact same one, so it's nice that you get a different practice question. So if you have access to this document, which you all should because it's on my website and it's free, you can click that icon and it'll take you to an additional example that's similar, or it might be the exact same example. Okay, so another thing that you might want to notice is this is the same definite integral that we were looking at in the previous example, except in the previous example we were approximating it using R4 and M4, but now we're going to find the exact value of this definite integral, which represents the net area between the function and the x-axis from the x value -2 to +2. So how do we do this? Well, let's start off with delta x. So we want to calculate delta x, which is equal to b minus a over n. Here our b value is 2, our a value is -2, and we're going to leave n as is because we're going to take the limit as the number of subintervals goes off to infinity. So our delta x is just 4 over n. The next thing that we want to do is we want to figure out what x sub I is. And the formula for that, recall that it's equal to a plus I times delta x. So in this case, our a value is -2. And then we have plus I times our delta x we just calculated was 4 over n. And I'm just going to clean this up a little bit and rewrite it as -2 plus 4 times I over n. Now, we want to use the Riemann definition of the definite integral. So this definite integral is equal to the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I times delta x. So we need to plug in a bunch of stuff. We need to evaluate the summation, and then last we need to figure out what the limit is equal to. So this is equal to the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I, so f of -2 plus 4i over n, times delta x, which we calculated delta x to be 4 over n. So now what we're going to do is we need to evaluate -2 plus 4i over n and plug that into our original function. So anywhere I see an x in my original function, I want to replace it with -2 plus 4i over n. All right, so everything inside of my brackets, I'm going to need to simplify. Also, I am missing another set of brackets because the 4 over n is included in my summation. So technically, if you don't have that, it is incorrect. So I'm going to go ahead and add in those extra set of brackets. And so now what we want to do is this expression inside my inner set of brackets, we want to go ahead and simplify that, which is going to take some algebra. So make sure that you're writing the limit at each step until you've actually evaluated the limit, and same thing with the summation. I'm going to go ahead and distribute the 3 in. So that gives me -6 plus 12i over n, and then minus, I need to square -2 plus 4i over n, and so you could either FOIL. I'm going to use the box method. I really like the box method. It's basically the same thing as foiling, just a little bit more organization. So I have -2, 4i over n, -2, and 4i over n. So -2 times -2 is 4. This is -8i over n. And then 4i over n multiplied to itself gives me 16i squared over n squared. And notice that -8i over n and -8i over n are like terms, so if I combine those, this should give me 4 minus 16i over n plus 16i squared over n squared. So I'm just going to go ahead and copy that back over here. And I'm also going to notice that I didn't write times 4 over n at the end. That's because what I want to do is n is not a variable with respect to the summation. The variable with respect to the summation is I, which means that I can actually factor 4 over n outside of my summation, but not my limit, because in terms of the limit, n is a variable. So what I'm going to do is I'm going to move the 4 over n here, and then I'm taking that limit eventually or later on. Okay, so now we want to continue simplifying the stuff inside of the summation. All right, so I've started rewriting, and I'm going to deal with my constant term first. So my constants are -6, and if I distribute this minus sign, that would be -4 and +2. So -6 minus 4 is -10, and then +2 should be -8. And then I have 12i over n minus negative. So if I distribute that negative, it would become positive. So plus 12 plus 16 is 28. And then lastly, if I take this minus sign and distribute it to that term, I get -16i squared over n squared. All right, looks like we're definitely making some progress. So now what I want to do is I want to apply this summation to each of these terms individually. And way back when we were learning about summations, there is a theorem that allows us to apply the summation to each of those terms individually. So if we do that, we get the limit as n approaches infinity of 4 over n times the sum from I equals 1 to n of -8 plus the summation from I equals 1 to n of 28i over n, and then minus the sum from I equals 1 to n of 16i squared over n squared. Okay. Another part of the section that we looked at in summations is that another theorem says that we can factor out constants outside of our summations, and the only variable we have in terms of our summations is I. So anything that's not an I, if we have an n or a constant, we can factor that out. So we have the limit as n approaches infinity of 4 over n. And then I'm going to factor out -8 from my first summation. That just leaves us with 1. And then my second summation, I can factor out 28 over n. And that's just going to leave us with I inside the sum. And then for my last summation, I can factor out 16 over n squared. And inside the summation, that would leave us with I squared. Okay, so now we want to get rid of the sigma notation by using that other theorem that we learned. So for the first summation, based on what we learned in the previous section, that is going to be equal to n. The sum of I, based off our theorem, that was n times n plus 1 over 2. And then our last summation, again, from our theorem, we should have these formulas memorized. That is equal to n times n plus 1 times 2n plus 1 all over 6. All right, so we're definitely making great progress. 28 divided by 2 is 14. And then n divided by n gives us 1. And we have an n here, and there's 2 n's in the denominator there, so I'm going to have an n there. And I can do 16 divided by 6, and both of those are even, so that would be 8 over 3. And then as a next step, I'm going to go ahead and distribute in the 4 over n to each of these terms. So if we do that, we have the limit as n approaches infinity of 4 over n times -8n would be -32, plus 4 times 14 is 56, and then in the numerator we'd have n plus 1, and then n in the denominator. And then our last term here, we would have 4 times 8 is 32, and then n plus 1 times 2n plus 1 over 3 times n would give us 3n squared. Okay, now at this stage, based off how we've simplified this, we can go ahead and just start to evaluate the limit. So let's go ahead and do that. If I take the limit of a constant, -32, that's just going to be -32. This fraction here, n plus 1 over n, if n is going to infinity, that's just going to go off to 1. So I have plus 56 times 1. And then minus, this is where we have to be really careful. So this is, once again, we're taking the limit as n approaches infinity of a rational function. And if I were to multiply out or FOIL out, n times 2n is 2n squared. So in both the numerator and the denominator, we would have quadratics, or they would be the same degree, in other words. So the limit as n approaches infinity would be the ratio of the leading coefficients. Students will often forget about this pesky 2 right here, so please be careful about that. If I multiply 2 and 32, that gives me 64. So really, I have 64 in the numerator and then 3 in the denominator. Let's do some simplification, and 32 plus 56 gives us 24. And then if we do 24 minus 64 over 3, that's going to end up being 8 over 3. So it turns out that our final answer for this definite integral is 8/3. Let's just rewrite that really quickly. So the exact value of this definite integral is 8/3. And if you remember from the last video and the last example, when we were approximating this definite integral, we approximated it in two ways. We found r sub 4, and we found r sub 4 to be 8, and then we also calculated m sub 4, which is using the midpoint rule, and we found that to be 3. And we made a comment earlier that if you are approximating a definite integral, usually the midpoint is the much better way to go than a right or left Riemann sum. And that holds true here because 8 over 3 is the same thing as 2 and 2/3. And 2 and 2/3 is much closer to 3 than it is 8. So m sub 4, or the midpoint rule, was a much better approximation. That concludes this example.